In this video, we're going to continue looking at photogrammetry techniques and Gaussian splatting for real-time radiance field rendering. If you watched the previous video, you'll be happy to see that the screen capture in this one is clearer. However, I'm now using my webcam to record the audio, so I'm not sure how that'll turn out. What we're going to look at today is a bunch of Gaussian splatted radiance fields rendered in Unity. The main workflow that we'll go through is one that I've been experimenting with over the past week or so. The idea is to take a 360-degree video, extract frames, convert those frames into flat images that can be matched in Colmap, Gaussian splat the resulting point cloud, and then bring that 3D Gaussian splatted radiance field into Unity for real-time interaction or rendering out video. It sounds like a lot, but it's really pretty straightforward once you go through it a few times. As a quick reminder, these radiance fields, which are basically point clouds, are not photogrammetry, despite some superficial similarities. The only reason to even mention photogrammetry and Gaussian splatting, or NeRFs, in the same sentence is that they are all ways of representing reality using a series of images. The fact is, very rarely would you expect to achieve analogous results from these methods. Photogrammetry is about creating a highly accurate and measurable 3D digital point cloud or surface mesh model, whereas NeRFs and Gaussian splatting excel at rapid, accurate representation, at least aesthetically, of an overall scene or environment, especially ones that would be difficult or impossible to capture with photogrammetry, such as highly reflective objects or large scenes that would simply take too much time to document through photographs. This video that's been playing is one of the scenes I'll walk through rendering. If anyone can name the location, leave that in a comment below, and the first correct answer will win a cool prize. I'll mail you a 3D print of this sculpture. For those of you new to my videos, I do a lot of 3D scanning and 3D printing of ancient Roman and Greek sculpture, so this would really be a one-of-a-kind print. Go ahead and put on your geoguessing hats and leave a comment. The first thing to know about Gaussian splatting is that it's quite GPU intensive. It requires a lot of video RAM. There are ways around that as described in the Gaussian splatting methodology paper, but it really slows down the training process. Processing that would normally take 30 minutes on the GPU can take 3 to 4 hours if you use the CPU for data storage. This scene we're looking at here is about 75 photos captured with a UAV and processed at full resolution on the GPU, which is an A100, and it basically maxed that out. The second thing to know is that the most time-intensive part of the process is actually the first step, and that's the camera pose estimation using Colmap. Colmap is a general-purpose structure from motion or photogrammetry software. I usually use Metashape for my photogrammetry work, so learning Colmap was kind of fun. And I'll point out some useful tips and tricks when we talk about that workflow. With that said, there are a number of cloud processing services like Polycam or Luma AI that have jumped aboard the Gaussian splatting hype train in the past few days. And they can generate Gaussian splat visualizations as well as NeRFs, if you don't have the necessary hardware. I don't really like giving companies my data for free, and figuring out how to do all of this on my own computer was pretty satisfying too. And I also learned a lot in the process. Later on, we'll compare some results from those cloud services to what I was able to generate on my home computer. Let's start out by looking at a few examples of Gaussian splatting so we can see where this method excels and where it falls short. Now, a quick disclaimer. I'm using data sets I've collected over the past 10 years or so for photogrammetry, which isn't necessarily the capture technique you'd want to use if a neural radiance field or a Gaussian splatted render is your primary goal. But for the most part, they work pretty well. And I'll point out what I would have done differently if this technology had been possible at the time of capture. In this Unity project, I've loaded in about 10 Gaussian splat assets that I've generated over the past couple of weeks. And I'll just toggle through these and talk about the number of images and what works and what doesn't before we dive into the workflow. This is important because not every data set is well suited to Gaussian splatting. So it helps to see good results and also the not so good ones. This first scene I would consider to be not a great result. You can see there's a lot of floating splats. It kind of has a hazy, cloudy quality, and that's because this was derived from about 1,000 frames extracted from a 360-degree video. And I simply walked down the sidewalk holding the 360 camera and took video. I then extracted those frames and ran them through the Gaussian splatting. A little later, I'll talk about the problematic qualities of using 360-degree data. You might recognize this one from my last video. This is Church Rock in Utah, and this, I would say, was a pretty good use case of Gaussian splatting. 4K video flying in an orbit pattern around this large rock structure, and I extracted frames and ran those through the Gaussian splatting method. This one is sort of interesting. I wouldn't say it's a particularly good result. This was an old photogrammetry data set. It was about 70 photos maybe taken with a full frame camera of this statue by Bernini. This statue is called Saint Sebastian, and there's a lot of these floating splats, these floaters that are making the scene hazy. Despite that, there is a lot of good detail in the sculpture itself, and you can see that the reflection on this highly polished marble is captured quite well, and in a photogrammetry model, that surface would have been all pockmarked and bumpy because photogrammetry has difficulty with reflective or shiny surfaces. And there's another reason that the Gaussian splatting doesn't work so well here on this data set, and that's because I took very specific photos of this statue without sort of a concern for the broader context of the room that the statue is in. And with photogrammetry, you're typically focusing on a single object. You want to get all the details of that object, where Gaussian splatting and neural radiance fields excel is capturing this much broader scene. In other words, they capture much more than simply the subject of your photographs or video. This next one is about 40 photographs that I took of this courtyard in Florence. This is the Palazzo Medici Riccardi. And here I was really concerned about capturing essentially from the column capitals up. And I wanted to create a photogrammetric model of this because I knew that I could sort of put a floor in and even rebuild the columns in a 3D modeling software if I wanted to, because a photogrammetry model is a surface mesh with a texture. However, here, the lower part of this scene really does not have that much detail, understandably, because I didn't take that many photographs of it. However, what's impressive about the Gaussian splatted scene here is that the upper part of the courtyard, the roof line, the sky, the reflections in those large windows, that turned out really well. So I was actually pretty impressed with this one compared to the photogrammetric model. This one is another data set that I captured with photogrammetry in mind. This is a Villa Medici, also in Florence. Here I was able to take photos from the ground, the center of this atrium, but also up where the camera is right now in these balconies. And the interesting thing about the Gaussian splatting model is that, in particular, that chandelier has a lot of detail on it that did not turn out at all in the photogrammetry data set. However, where the Gaussian splatting, and we can really see it here when I zoom into the walls, where the Gaussian splatting tends to not work so well is when you get very close to some of these detailed elements, like, for example, the paintings, the frescoes on the walls of this atrium. As you get closer, it just kind of falls apart. Yet at the same time, it does pick up some very fine detail on these trophy heads of these deer. So we're getting the antlers, we're getting a lot of detail that at the same time didn't come out in the photogrammetry model. However, because the Gaussian splat is basically a point cloud, as we move closer to some fine detail on surfaces like these frescoes on these walls, they look okay from right about here, but as you get closer you start to be able to discern the splats. And that's simply because, again, this is basically a point cloud, but instead of points we have these blobs of color. So without having some sort of iterative, maybe a level of detail where it adds in more points, more splats as you get closer, it tends to kind of fall apart. And to give you a better idea of what that means, we can turn off the splats and just visualize the PLY point cloud, which is essentially the key points that were found through the image matching in Colmap. So if we visualize just the points, that's what we're looking at now. And then we can turn the splats back on, and what these splats are, again, are colors that have been trained based on the input data, the photographs. Let's say you have a 360-degree video that you want to process through Colmap and Gaussian splat. The 360-degree or equirectangular data is great because it allows you to capture very quickly a huge scene. So in this case, I'm walking down a street carrying a Insta360 1R, and this is a video that I took a few years ago in Italy. And if I had the intent of capturing this data for photogrammetry or Gaussian splatting, I probably would have held this over my head so that my body is not blocking a large part of the scene. The downside to data like this is that it's not very high quality. It's pretty low resolution because you're cramming an entire scene into a sensor that's not very large and an overall resolution that's not very large. For example, this is a 5.7K video resolution, and it's capturing an entire scene, whereas for example, a 5.7K or 4K or 8K frame camera, so a traditional mirrorless or DSLR or video camera, is going to collect at 8K resolution just a scene like this, rather than having to spread that data out over an entire 360-degree view. So in other words, cramming a 360-degree view into the same resolution that with a normal camera you would get this single view like this. Of course, the benefit to this 360-degree capture, despite the low resolution, is that I am able to document this entire scene just walking down the street. If I was photographing this street for the purposes of photogrammetric capture, I would have to work very slowly down one side of the street, taking photos or videos of the opposite facades, and then come back up the street shooting the other way, as well as capturing the street itself, the ground, and shooting into any sort of doorways or nooks and crannies that I wanted to capture as well. It would be very time consuming, and it would generate a huge amount of data. This way, you can simply walk through a scene, capturing everything around you with the spherical camera, and although the quality will be lower, it's going to be very quick. So this points to another one of the benefits of Gaussian splatting of scenes. It's very fast, it allows you to get a very quick representation of a complex scene, and then you can explore it virtually after you are no longer sort of on location. Now, in order to use our 360-degree video for a Gaussian splatted scene, we need to first extract frames from it and then turn those frames into flat pinhole cameras, which is what Colmap calls a sort of normal flat image. And the way we're going to do that is using Nerf Studio, which has a built-in script to ingest equirectangular video or imagery and then output these sort of cube maps. But they're not really cube maps because they need to have enough overlap to be matched in Colmap. So they're really it's going to take every equirectangular frame and split that into 8 flat views that roughly correspond to top, left, right, front, back, down, or up, down, left, right, front, back. And then those can be matched in Colmap in these sort of scan station, camera station type ways. And what we're looking at here is a visualization of all those camera locations, the locations of the frames of that 360-degree video where I was walking down the street, and those have been extracted and then matched, and we're seeing a representation of the very narrow street that I was walking down here. In order to process equirectangular data in Nerf Studio, first you want to follow the installation instructions for Nerf Studio. It's fairly straightforward. And then you're going to use this ns_process_data command. And you need to specify an equirectangular input. You can tell it how many images you want it to extract per equirectangular frame, 8 or 14. If you do 14, there's going to be more overlap, and that'll help with alignment in Colmap. And you can also give it a crop factor if you were holding the camera over your head and you want to crop yourself out of the frames. And then specify an output directory. So it can do this with images and also videos. And even though we won't be using Nerf Studio to actually do the Gaussian splatting, this is a really handy script that is built in here, and you can essentially just use Nerf Studio to process your equirectangular data for Gaussian splatting. Once you've used Nerf Studio to process your 360-degree data, you'll probably have about, depending on the length of your video clip, you'll have 700 to 3,000 images that then need to be aligned in Colmap. And the Gaussian splatting methodology that we'll be using requires a Colmap sparse cloud, which is what we're looking at here. And it also requires that the camera models be processed using pinhole or simple pinhole, which are 2 of the camera models in Colmap's feature extraction window here. So there are basically 3 steps that we will use Colmap for. Those are processing feature extraction, where you want to specify a simple pinhole, processing feature matching, where it will match all of the points found in the photographs, and then reconstruction, start reconstruction, and that's what builds the sparse cloud that we're looking at here. Now, two things that I have noticed in processing these data sets with ColMap. Feature extraction, use simple pinhole. However, they recommend in feature matching that you use exhaustive, and that takes a really long time. But because that's where it matches, it compares every single image to every single other image. Because we extracted these from video, and because of the naming conventions of those frames when they are extracted, we can use sequential feature matching. And this will save a lot of time. I would say it cuts the time spent on matching way down, from hours to maybe 30 minutes to an hour max, depending on the speed of your computer and the number of photos you have. Suffice it to say, it's much faster than the exhaustive matching, and it gives you basically the same result. If using sequential doesn't work, only at that point would I suggest using the exhaustive matching. So definitely use sequential. Once you've done that, you click Start Reconstruction, and this is the really time-consuming part because it adds all of these images into this cool little viewer here, and you'll see it iteratively add cameras in and project the points that those cameras are seeing. Once you have a final sparse point cloud here, this one, for example, is 975 images, frames really, from that equirectangular data, and this took about 3 hours. Once you have this, you want to go to File, Export Model, and then you'll follow the folder structure that is recommended in the Gaussian splatting methodology. So you'll get everything you need for that right out of ColMap here. Then you'll take that sparse cloud, the sparse model as ColMap calls it, and you'll feed that into the Gaussian splatting. Okay, so I've just finished training the dataset that we extracted from the 360 video, processed through Nerf Studio, aligned in ColMap, and then ran through the Gaussian splat method. This one was about 3,300 images extracted from those spherical frames. And I'm now in Unity, where we can visualize that Gaussian splat asset. So the first thing you have to do whenever you load a new one of these is almost always to correct the orientation here, because these don't have any orientation by default. At first glance, this one, it looks nicer than the other one, the previous one. So this is it running in real time. Of course, you can also set up a camera path and render it out. I forget where exactly I walked here, but I think it was through this sottopassaggio. And we can see one of the problems with these Gaussian splatted point clouds, radiance fields, is that if you don't exactly follow the camera path, you tend to get these foggy splats that interfere with the viewing. So it's not, in some cases, particularly pleasant to look at, and I think that has a lot to do with the input data. So again, spherical imagery is not ideal, but also it has something to do with as well, I'm sure, some of the parameters in Colmap and of course the type of scene that you're in. So here it does not work very well when we go into this narrow passageway. We get a lot of these splats that are sort of floating in the air that interfere with our camera here. Let me see if I turn down the splat scale. That helps a little bit. Still, it's not particularly beautiful. I apologize for my keyboard clicking while I'm navigating around the scene here. Now, of course, if we compare this to the photogrammetry data, I'm not going to use the exact same data set, but I'm going to use a similar one. You can really see the difference between a Gaussian splatted point cloud in Unity and a photogrammetry meshed model in Unity. Now we're looking at a photogrammetry model that has been textured, so a textured mesh surface model in Unity with a Unity camera moving through it. Of course, this has been rendered out to image frames, so it is more of a video rather than me interacting with it. But it gives you a sense of the difference between the Gaussian splatted visualization and a photogrammetry model in Unity. And you can see we just went by some texture issues there, but in general, the 360 data doesn't really work so great for both. Let's end with an example of what I think is a really nice visualization of a Gaussian splatted data set. This is rendered out of Unity, and it's about 130 photographs that I took of this sculpture, which is in the Louvre. And this, I think, really exemplifies where Gaussian splatting brings something to the table that you can't get with a photogrammetry model. In the photogrammetry model of this statue, which I'll show in a moment, we're really only able to see the statue itself. It's an isolated object. We don't have this surrounding scene, the context of the gallery that it's in. And we're certainly not getting the reflections on the floors, the reflections on the marble itself, this nice diffuse baked-in lighting, all of which we're getting with this Gaussian splatted model here. Which is all to say that I think there is a use in some cases for these Gaussian splatted models over photogrammetry. For example, if you wanted to do what I've done here, which is create a sort of cinematic experience of this sculpture versus what the photogrammetric model would give you, which is a more analytical object in hand type of experience where you're really analyzing the object itself. You don't want the distraction of the surrounding scene. Once again, if you've made it this far, thank you. Hopefully it was entertaining, educational, and at least enjoyable. If you have any questions, feel free to leave a comment below, and stay tuned because I hope to keep on putting out videos like this. Some of them I hope will be less of me talking and more cool visuals for you to enjoy, and that also highlight some of the different use cases for these technologies, whether it's photogrammetry, Gaussian splatting, neural radiance fields, and whatever comes next. See you next time.